right. Hi, can you all hear me?
Yes, hello.
Good, great. So then let's get started. So just a few words on where we left off last time. So we were basically looking at representations of the conformal group. Of course, we also worked out the details of the conformal algebra first and so on and so forth. But this is the main point that we're going to start off from. So what we basically pointed out was that thanks to the conformal algebra, there are these essentially raising and lowering operators, k mu and p mu. And I argued, although I haven't yet given a proof of this, that the structure has to start somewhere, if you want, from below. So there is a given operator in a given conformal representation that sits at the bottom of this ladder here that we call the primary operator O min. And this primary operator is, of course, the one that is annihilated by the k mu. And then on top of this primary operator, we can act potentially infinitely many times with the raising operator p mu. And every time we raise it, we make a new operator. So O here goes to psi, goes to phi, goes to chi. In each time we act, we raise the conformal dimension. So let's say the conformal dimension of O is called delta. We raise the conformal dimension by 1 unit, which essentially just follows from the commutation relation of k and p. So psi has conformal dimension delta plus 1, phi delta plus 2, and delta plus 3, and so on. All right, so this is one idea. So we basically are building these conformal families, as we call them, by building them on top of a given primary operator that is now characterized by its conformal dimension delta, as well as its spin content, so its Poincare content. So the primary operator, okay, okay, here I called it phi alpha. Sorry, actually I can, yes, it's probably best to, well, okay, O min, and so then we say this O min, okay, in particular is our phi alpha below. And so this is characterized by having some scaling dimension as well as a content in Lorentz spin. So for example, this could be a scalar, in which case this S mu nu is just trivial. It could be a vector and could be a spinner. And I pointed out those two representations in particular, how you can implement them. And well, for such an operator, then we were able to work out how the conformal algebra acts in particular at an arbitrary point x. And so, for example, you have the dilatation operator that gives you not only the conformal dimension, which is a property by definition, sort of an intrinsic property, but it also gives you this coordinate-dependent dilatation, well, coordinate influence on the dilatation eigenvalue. Similarly, the angular momentum operators, they give you the intrinsic property plus some property that is like orbital angular momentum. And then for the special conformal transformation, well, things are a little less intuitive, or maybe just because we have less exposure to it, but you essentially also get this contribution here, which we argued happens in sort of the intrinsic behavior on the conformal transformation, and then you get these two contributions here if you translate away from the origin. Now let me just remark that you may or may not have noticed it already. I put the problem set on the Moodle page, and one of the exercises for this problem set is to derive, for example, this thing here, or at least some terms. And there are other exercises that are related basically to these kind of ideas, but exercises that have to do with, for example, proving bounds on the conformal dimensions, which we're actually going to go through in some well, less explicit detail than you're asked to on the problem set in today's lecture. So no, this was your view single page, always better. Okay, so let's move on then. So what I wanted to start off with is I wanted to make some comment on finite dilatations and then move on to this idea of radial quantization. Because actually radial quantization and dilatation, particularly the dilatation operator, are intimately related. So let me, yes, comment on finite dilatations. So the transformation in a dilatation is basically this one. So x goes to some rescaled coordinate x primed, which is given by rescaling the lengths lambda times x. And of course, in infinitesimal dilatation, we could write as 1 plus alpha, where alpha is small, times x. So we have here lambda is taken to be 1 plus alpha, obviously, with alpha very small, let's say. Okay, so now let's just make one of those comments that we've made before on the unitary operator that implements the dilatation. Okay, so UD of some parameter alpha. Okay, so small parameter alpha. That of course satisfies, just from the group property, that U dilatation of alpha 1, U dilatation of alpha 2. Okay, that's the same as the dilatation by alpha 1 plus alpha 2. And as we've seen a couple of times now, every time this kind of thing happens, then you can just simply exponentiate it. So the finite dilatation then, finite dilatation operator, okay, U of lambda, well, it's going to be something like U of lambda, oops, chopped into n bits raised to the power n, which is the usual 1 minus I lambda over n d to the power n. And so in the limit, in the limit n goes to infinity, we just find that ud of lambda is e to the minus I lambda d. So that's something that's very familiar to you by now, but I just wanted to make a note of this because we're going to use this operator and when it comes to radial quantization. And so I just wanted to have it written down. Okay, so how does it act on the field? Well, we can actually work that out. Okay, so let's see. Consider, for simplicity for now, a scalar phi. Okay, so in other words, the S mu nu matrices act trivially on it. Okay, so then as usual, we can write phi primed of x. That's now going to be U dilatation phi of x, U dilatation inverse. Okay. And so to linear order, we can write this as phi of x minus I alpha, and then we get here, as always, the commutator with the generator, phi of x, okay, and then we can be explicit if we want to write alpha squared here. Okay, but we know, we worked out what this guy here is. Okay, this guy is I delta phi plus x mu d mu on phi, right? So let's write that out. As usual, I think it might be useful to take that on the other page. Copy, paste. Okay, so that's equal to, well, it's equal to phi of x. So plus alpha delta phi times phi of x. Okay, why? Because we had minus I, and then this guy gives plus I delta phi. But then, of course, we also have the alpha x mu d mu phi plus this order alpha squared term. Okay, but now you can just, with hindsight, or you can convince yourself that this is, of course, the same as the linear approximation to phi of x plus alpha x times 1 plus alpha to the delta phi, okay, plus the order alpha squared. Okay, so if you expand this to linear order from this term, you get that term, and then of course the linear order of this will give you alpha times x mu d mu phi. Okay, and then that's all the linear terms. So one deduces, therefore, this corresponds to the finite transformation. So phi primed of x is equal to lambda to the delta phi times phi of lambda x, or if we want to write it in a more convenient form, phi primed of x primed is actually equal to lambda to the minus delta phi of x. So this is our finite form of the dilatation. Okay, and this is probably something that many of you have seen before. But what it says is that if I transform such an operator, a scalar operator for simplicity now, but if I subject it to a dilatation operation, then it transforms itself with a certain scaling weight. Okay, and so if you want, this is the a posteriori justification for calling delta the scale dimension, or the scaling dimension, or the conformal dimension. Because if you apply the dilatation to a field according to the rules that we've worked out, what you find is that the field itself picks up a prefactor, which is precisely the scaling length raised to the power of what we call the scaling dimension. So that makes sense. Okay, but what it also allows us to do is, for example, let's look at something like how, let's just look at an example of a theory that respects this scale invariance in a Lagrangian form. So comment, or if you want an example. This is actually a useful example that we will return to later, but for now, you will see why we return to it later, of course. But for now, let's just see it as an example of how this works at the level of a Lagrangian. Okay, so let's write the following action for this field phi. Let's just write d dx, and then just the kinetic term, so the free scalar field phi of x, d mu phi of x. Let's see what happens under such a scale transformation. Well, under this dilatation operation, okay, this goes to, well, we ought to change, of course, the integration variable x primed. So that'll come with the Jacobian factor. And then all the derivatives change. So allow me to write mu prime. This means d by dx primed mu, okay? And then phi primed of x primed, and then d mu primed phi primed of x primed, okay? But now we can just count up what we get. So that's equal to d dx times lambda to the d, okay, because this comes from x goes to lambda x. So if I raise it to the power d as I do in the measure, I just get lambda to the d. Then I get minus 2 delta, okay, because each of the phi's goes with a factor of L lambda to the minus delta, okay, so 2 delta. I suppose we could write it as delta phi as we did before, but then also each of the derivatives, okay, gives me one more factor of 1 over lambda because it's 1 over length if you want. So minus 2 times d mu phi, d mu, oops, it's ugly mu, d mu phi, d mu phi. And now this is invariant, meaning the transformed action is equal to the original action if delta satisfies the equation d minus 2 delta minus 2 is equal to 0. So what we conclude is that this is invariant if the conformal dimension delta is equal to d minus 2 over 2. And that's good because you can convince yourself that this is, of course, the classical or engineering dimension of a free scalar in d dimensions. Let me write it here. This is sort of the engineering dimension of a classical scalar in d dimensions. Okay, and because this is a free field, I mean, this is sort of the most trivial example, right? But because this is a free field, of course, it also isn't going to pick up a anomalous dimension. So this also is a quantum conformal invariant theory. In general, of course, just as a side remark, because I've said it now, the real challenge is to write a theory that is a quantum conformally invariant theory. And that's a much more difficult thing than to write down a classically conformal invariant theory because fields can pick up anomalous dimensions. So finding examples of quantum conformal theories is much harder work. Yeah, okay, let me leave it there. So the final comment I want to make, or I just want to explain how to generalize this. So more generally, okay, so let us define the matrix J alpha mu, or well, it doesn't really matter. It could also be J mu nu, but this is basically the dx primed alpha dx mu. Okay, so the change of coordinates more generally, I'm still changing x to x primed, of course. Okay, then if we find if we have a field that has carries Lorentz indices, so let's say alpha 1 up to alpha L of x primed, so the transformed field phi primed, okay, this changes as the determinant of this thing to the minus delta over d. Do I have enough space? No, I need to squeeze in the next line. And then each of the indices picks up one factor of this Jacobian. So alpha L mu L phi of mu 1 mu L of x. Okay, and then we have the determinant of this Jacobian. Well, one of them we've already worked out. This is the case of the dilatation. lambda d for dilatation. Okay, and you can just work out. So if this gives me the, so for a scalar field, right? I have no no factor of this matrix here, but the determinant of j to the minus delta over d gives me lambda to the minus delta, which is, you know, this transformation here and the one that we used to work this out. Okay, so that checks out, and you can convince yourself that that's the correct way of generalizing this for a field that carries spin. And then the other thing which we haven't done, but which I'm just going to state here, is that on the special conformal transformation, that G takes a specific form, which is 1 minus 2 x dot b plus b squared x squared to the power minus d for special conformal transformation. And obviously the way to work this out is exactly the same as we did for the scaling transformation, right? So you look at the unitary operator, you see how it acts, and then you well, deduce the finite form, and well, you go ahead and you find, for the scalar field anyway, it's easy to do, and then to generalize it to several indices is kind of the same thing here. 1 second, I wonder if, okay, very good. Right, so that's, so then using this rule here, okay, using this rule, you can easily build a classically conformally invariant theory based on such fields. Using these rules, can build classically conformally invariant. Classically conformally invariant field theories. But I emphasize again, quantum conformal field theories are a whole different ballgame. But of course, the one that we're eventually moving towards. So that's all I have to say, in fact, on conformal algebra, let's say, and how it acts on our operators and how it acts on fields, although we will get back to this in a different context fairly soon. But what I want to do now is I want to move on to this idea of radial quantization. But maybe before I do so, maybe a good moment to pause for questions, if there are any. So far so good, excellent. So now let's go to radial quantization. This may look a little bit unfamiliar at the beginning, but it's something that is easy to get used to. Radial quantization. So let's just make a geometrical remark on what standard quantization is. Okay, so standard quantization well, you have some time slice t, and on that time slice you specify a state. So that works because you have a copy of the Hilbert space on a time slice. So I'm writing on each time slice, because there is also this unitary operator, which is time translation. So u of, let's say, delta t, which evolves this time slice to a time slice, let's say, in this case, in the future. And you also have a copy of the Hilbert space, of course, on this time slice. And the unitary time evolution operator is just a map in the Hilbert space that gives psi, maps it to its time-evolved version psi of t. And this corresponds to a time-like foliation of your space-time. So the important part is that u of t, the unitary operator in general that implements this, this going from one leaf of the foliation to another, is just e to the minus I times the Hamiltonian times time. So this is the Hamiltonian. And well, we could also write this in Euclidean. So this is e to the h times tau, where Euclidean time is minus I times t. All right. So this is usually a very convenient choice. And one reason why it's a convenient choice is the following, is that if you start with an energy eigenstate, so any energy eigenstate En of t, then under this evolution with respect to the Hamiltonian, what you find is it's just an inessential phase, e to the I En times t, but in particular, you remain in that same eigenstate, okay? But in actual fact, in the CFT, we're not going to label our states like that. We're going to label our states by their conformal dimension and by their Lorentz content, by their spin. So it actually turns out that that suggests that there is a different, much more convenient quantization, as I will point out now. So, but okay, for CFT, we label the states, let's say, by the eigenvalues of D, okay? I mean, just for suggestive reasons of suggesting this, this is, of course, En is an eigenvalue of H, the Hamiltonian, right? So this, I think I've basically been previewing this already last time around, but this is, of course, also kind of suggestive that maybe there's a quantization in which we think of D as the Hamiltonian, okay? So let's go there. So first of all, so let's construct eigenstates of D for now, and then we will see what happens to them under conventional time evolution, which we will say is not convenient, and then we will see what happens later. We will see what happens under this radial evolution, which will be much more convenient. So, all right, so let's construct eigenstates of the dilatation operator. That's actually very easy, thanks to the power of the conformal symmetry. So let's construct eigenstates of the dilatation operator. So just consider the following object, psi, okay, which corresponds to a state that is obtained by taking a primary operator O at the origin and to act on the CFT vacuum, meaning the one that's annihilated by K here. So this is our primary. And this is our vacuum state, the lowest state if you want. So now what we would like to know is what happens if I ask psi, what is your D eigenvalue? Well, that's of course equal to D acting on O of 0, 0 by definition. And so this I can write as D commuted with O acting on 0 because D annihilates O. Okay, but then I use my conformal algebra and I know that that gives me the delta acting on 0. Okay, so delta being the delta of this operator O. Okay, so yeah, let me write this. Well, I mean, sorry, I guess this is kind of obvious that that's what that is because I've used this commutation relation here. Okay, I hope the notation is obvious. I hesitate a bit calling it delta O because well, I called this state here psi, so we could also call it delta psi. Let's just call it delta. Okay, and it's what delta is defined by this equality here. And so what we've done is we've associated. Yes.
Commutator of d with phi naught is delta times phi naught, right?
Yes, which is why very good, which is why this of course has a psi here. Thank you.
Okay.
Very good. So let's make it totally yes. So this commutator is the same as I delta O of 0 acting on 0. Okay, but O of 0 acting on 0 is what we called psi. So very good. That's of course extremely important, but that's also why why the state psi. If I ask it what is your dilatation eigenvalue, well, it's going to be the dilatation eigenvalue of the operator O. Okay. Good. So this means that to the operator O, we have associated a state. Okay, and that is what in the CFT language one usually refers to as the operator state correspondence. So there is here at this level, there is a correspondence between an operator, primary operator O that I act at the origin and a state psi. But we will put a little bit more meat on this whole operator state correspondence in a little bit today, actually. Because in order to make this, well, we can give this a little bit more meaning by indeed going to the radial quantization. I think Adrian had a question.
Yeah, so it's a quick question. So far at this level, do we have any constraint on the reality of the scaling dimension, or can it be something complex, for example?
I believe that at this point, we have no constraint on the reality of delta.
So we cannot say so far that D is anti-emission, for example.
I don't think so. I need to think about this, but I think this comes from constraints like unitarity, or if you say it in Euclidean space, reflection positivity.
Okay.
Okay, so good. So psi, and in particular psi, is an eigenstate of D, thanks to the correction that Arunaba picked up on, because D on psi gives you I delta times psi. Okay, so now let's see what would happen if we evolved such a state with a Hamiltonian. So if we did the ordinary time evolution. So in order to see that, actually one nice way of doing that is, let's act with U is equal to e to the minus I x mu p mu on psi. So I've sort of covariantized, if you want, the action of the Hamiltonian. The zero component of this is the Hamiltonian. You'll see that the same conclusion will apply if we really if we choose this, for example, to be just a vector that is really just along the time direction. But the expression is more obvious in the meantime if we act with the full P. Okay. So then psi as a time evolved state psi tilde, okay, this is equal to time evolution operator U now. Yes, okay, I've defined it to be U. Okay, I can call that maybe UP, acting on psi, okay? And then that's of course equal to, well, just expanding this exponential I x dot p to the power n, oh, these brackets aren't working, to the power n divided by n factorial, okay, on psi, n 0 to infinity. And now you see what happens, because x dot p to the power n generates all possible descendants of psi. So in particular, they will have all sorts of conformal dimensions, right? So each time I act with a p on psi, I generate a descendant. And in fact, I generate, because this sum stretches over all n, I generate all possible descendants, okay? And so therefore, it's clear that psi tilde is no longer, is not, oops, an eigenstate of D. So that means that if I just want to label my states with conformal dimension, which is what we just said is conformal, which is a good way of thinking about a conformal primary and therefore the conformal family, this is not a good way of thinking about time evolution. And so there is going to be a better way of thinking about time evolution, which is going to be this radial evolution. But that's just to say that the usual time evolution is in some sense inconvenient. And why even time evolution? Because, well, as I said already, time evolution, you can also just say that, well, you only ever act with P0, okay? And this will just be, you know, one of the, a projection, if you want, of every possible descendant. It's just nicer to write it here in this covariantized form, because it's then obvious that you act with the full P. But of course, even if you just act with the zero component, you generate projections onto all possible descendants. So even strict time evolution falls into the class of those things that we've just said are inconvenient here. So let's, so with this little side remark, let's now move on and talk about what is the more convenient choice. Okay, so more convenient choice. So this will be the radial quantization, and as I already said, that will at first seem a little bit unfamiliar, but then actually after the break, we will go to a perspective in which this actually starts looking much more familiar, which is possible to do thanks to conformal symmetry. But so let's switch for a little while now to just Euclidean. Okay, so we now work for the purpose of this section, we work in Euclidean signature. So let's work in RD. Right, instead of R1 comma D minus 1, let us work in RD. And so the metric is just trivially the flat metric. So it's dxi, dxi. So contracted with respect to the Kronecker delta symbol. But what I can do, of course, I can choose one of these. I can choose a radial direction, the length of the vector, xi, and I can write this as dr squared plus r squared, and then I have the leaves of the foliation are d minus 1 spheres. Okay, so this thing here, this is the metric on a unit d minus 1 sphere. So before we had a foliation by slices, okay, time slices. You can of course do the same with Euclidean time slices. But here now what we're doing is we foliate by spheres. So you can picture it as the origin, and then you have concentric spheres, okay, which go radially outward from the origin. Okay, and we have the radial vector R, and each of these leaves is one of my SD minus 1, like this leaf here. I should have drawn it in blue in the first place, but okay. So you see what I mean. So these are SD minus 1, let's say, of increasing radius R. Okay, why is that? Because on each R, as he said, we put a unit SD minus 1, and then its physical size is given by this R squared here. So to draw back the line to what we had before, this is a foliation. So now we're foliating RD by spheres SD minus 1. We're of course free to do that. This is just right now on the level of the metric. But our goal is then to have a copy of the Hilbert space on each SD minus 1, and to evolve from S to the D minus 1 to S, inward or outward, let's say toward increasing R. Okay, and so the question is how do we do this? And the answer is evolve with the dilatation operator. So I would like to show you why that works just before the break. Okay, so what we have is we have the dilatation operator D. This can be written as minus I xi d by dxi. Okay, in these dxi coordinates. Okay, if you want, this is just the Euclideanized version of x mu d by dx mu. Okay, and Euclidean going to Euclidean signature just means that the zero component the zero component becomes I times tau, but because I have I times tau in the numerator and the denominator, the factor of I cancels out, so it's really the same. So it's really the Euclidean version of I x mu dx mu, excuse me. Okay. But now R, the length of the vector is obviously just the root of xi. The length is just the square root of the length squared. And so then changing from xi to R, we find is that I d by dxi is actually equal to R d by dr. You can convince yourself that this is correct, which we can write as d by d log R. So this we'll take on the next page. Now it's just a couple more lines before we're there. So I have this relationship here. I remind you. So my conclusion, well, we know, of course, sorry, I mean, geometrically, of course, it's obvious that d is equal to minus I r d by dr moves from an s d minus 1 at radius r, let's say, to an s d minus 1 of radius r plus a small dr. Okay, it moves radially outward. Okay, but what does this correspond to? Well, this corresponds to the evolution operator e to the minus I d times log r. Okay, so the operator that implements this is the dilatation operator with respect to radial r. And why is that? Well, this I can just quickly say. Consider the following, okay? So go back to something that's familiar. Always we say the Hamiltonian is the generator of time evolution. So what we have there is we have something like I d by dt, right? That's the tangent vector to the time direction, okay? That's corresponds to an evolution with e to the h times Euclidean time. And then what we have is I d by d log r, okay? This is going to be related to e to the minus I d log r. So the comment that I want to make here, well, it's twofold, but let me only say the first because we're running out of time. We'll get back to the second after the break. The point is that d by dt, right? Well, okay, let me just, yeah, but I'll go to the Euclidean case after the break. Okay, I don't want to confuse you too much. So what is here in the denominator is basically what multiplies here after the operator. So what we have here is that we have d by d log r. Okay, so log r must come here. So time becomes log r. And then the operator that implements this is the dilatation operator because it's r d by dr here. Okay, so it's precisely the dilatation operator times log r that gets you from one sphere to a sphere of just larger size. Okay, so I'll get back to the factors of I that are a little bit subtle after the break. Let's just forget that that seems to be an issue right now. There is a resolution. So let's break. Of course, I'm happy to answer any questions. Okay, well, seems all is good. So I'll see you at 3:15, okay, on the other link. Bye.
Yeah.
Okay, now, so back to the factors of I. And the factors of I, basically for this, let us remind ourselves that we're in Euclidean RD. And that we've worked out that the time evolution operator, so the radial time evolution was e to the minus I d log r. And I remind you, so this is a notion of Euclidean time because we're in Euclidean RD. So this is definitely Euclidean time. And this factor of I came from the definition of dilatation. Okay, so we had basically u d, which was something like 1 minus I lambda over n d to the power n. And to be precise, we took this in the limit. Okay, but this we should compare to Euclidean time evolution, the usual Euclidean time. So let's call it the just Euclidean time. Okay, Euclidean time evolution. which is e to the ht Euclidean. And so this means that what we should compare is indeed minus id and h. So the Hamiltonian with respect to which we study the radial time evolution, or just radial evolution, is minus I times d. And this should be seen as the analogy to the time evolution in Euclidean signature. Okay. And see, therefore, it's also the fact that because the dilatation eigenvalue is I times delta, okay, then as we shall see, the reality is a reality on delta itself. Delta will be real. Okay, so however, now let's actually go to this slightly different perspective, which will be, which in some sense will make this radial evolution much more familiar. So for now, I remind you again, what we were saying is that in Euclidean space, nobody tells us how to foliate things. We can essentially do what we want. There isn't an intrinsic definition of time in Euclidean space, and there is a convenient time evolution that preserves the dilatation eigenvalue, and that's this radial evolution. But let's actually see that using the power of conformal symmetry, we can actually think of what we just did as a much more plain vanilla time evolution. Okay, so, and this comes actually from the identification of time as log r, Euclidean time as log r. So let's see, so maybe I'll say plane to cylinder. So plane is RD, and the cylinder will be what we will find now. So identify evolution. So let's call a time variable tau to be log r. Okay. But of course, let's just see what happens to our metric if we do this. So we have the plane dr squared plus r squared d omega d minus 1 squared, so our foliation. But now if I change r to e to the tau, okay, then this just becomes e to the twice tau times d tau squared plus d omega d minus 1 squared. Because if you want, it's dr over r, which gives you d tau. No, it's r dr that gives you tau. And so you can, no, it is dr over r, excuse me. So you can factor out the r squared, which is e to the 2 tau, and then you get dr squared over r squared, which is just d tau squared. Okay, but now the metric that we have found is precisely the cylinder. This is what we call the cylinder. The cylinder being the real line r for the time variable tau times sd minus 1, right? So this is some cartoon of it. I can write like this. I have I just draw a finite section in time. So this tau goes up here, and then each of these things is an sd minus 1. So I'm drawing the case d is equal to 1, where the sphere is just a circle. The one sphere is just a circle, but you know, in general, you just have at each constant time you have a full d minus 1 sphere. So these two sections that I wrote here are both d minus 1 sphere. And now what does actually this time tau do? Well, the evolution in tau moves up and down that cylinder. The cylinder. And in such a way, such that, well, if tau goes to minus infinity, So I'm in the infinite past of the cylinder. Well, this was actually radius goes to 0 in the r variable, okay? And if tau goes to plus infinity, so I'm in the infinite future. I mean, this is of course still Euclidean time, okay? So I'm using future and past in the Euclidean time. This was the same as r going to infinity. Okay, so this, well, first of all, now I really have something that looks much more like time evolution, right? I really have a cylinder and I have this real direction time and I go from minus infinity to plus infinity. And that's exactly the same as going out from the origin to increasing larger sizes, okay? However, this also gives a little bit of a perspective on this operator state thing, because we said that, remember, we constructed the state by inserting an operator at the origin. So operators inserted at r is equal to 0 are in the infinite past on the cylinder. Okay, so and if you want, just correspondingly also operators inserted at r goes to infinity are in the infinite future.
Sorry, Julian.
1 second. Yes.
So is it legitimate to speak about past and future if we are still in an Euclidean cylinder?
Why? I was just saying that this is just the value of tau that is plus or minus infinity, but it's not time as we perceive it.
Sure. Okay. And I had just another question, because I always get confused about this. So about the prefactor that we got before the cylinder metric, can we drop it and forget about it?
No, we can't in general drop it, because that would be violent variance. But in 2 dimensions, for example, you can just drop it. Okay, so and here we evolve with the Hamiltonian. Well, yes, well, we can put it in inverted commas. H is equal to minus I d. Okay. What did I want to say? Yes, sorry, I did want to finish this comment. Yep. So I wanted to say that, why does this give you an illustration of the operator state correspondence? Well, I think it's just a nice illustration that the point that I'm making is that you insert this operator at the origin. From the cylinder perspective, what that means is you prepare your theory in the infinite past in that state corresponding to the operator. So that state we call the psi, and then you evolve with that state. And equally, if you had an operator insertion at infinity, that would mean that you put sort of an operator at the infinite future. So these would be sort of the boundary conditions. You have the bra here, and then you have the cat there, and you basically look at the evolution with respect to those states. And the final comment that I will make is that you might remember that the spatial conformal transformation had something to do with exchanging 0 and infinity on the plane. And so it's true that 0 is a special point. We've already seen that. But for essentially the reason that I just said, infinity also is a special point. We haven't yet quite seen that, but we will get back to this. Okay, this inversion operation actually plays a very important role. And so 0 and infinity are two distinguished points, and it's actually very natural to insert operators there even on the plane. But from the cylinder perspective, I think it's even more organic because you have it in the infinite past and the infinite future, Euclidean time. All right, that was the remark that I wanted to make. So now the Hamiltonian is minus I delta. And so I delta, so Hamiltonian H is equal to I delta. This has real eigenvalues. Because of the various factors of I. Okay. Right, so there is this factor here, but then D itself, the eigenvalue is I times delta. And so now this identification here means that a well-defined CFT better had delta bounded from below. Because if it didn't, then this cylinder quantization would make absolutely no sense, right? So in this cylinder, we really have a theory whose Hamiltonian is minus I delta, and we have time evolution just like we usually think about time evolution. So that's a perfectly natural theory. And so this theory just wouldn't be well defined unless its energy eigenvalues, which are now the eigenvalues of minus I delta, are bounded from below, because you know that quantum mechanics with a spectrum that's not bounded from below is not well defined. And so this basically is one way of seeing that conformal dimensions must terminate at some point, which if we backtrack means that if we try to lower a given delta further and further with k, we must at some point hit a lowest step on the rung, lowest rung on the ladder. Excuse me. Okay, so let's go on now a little bit and learn some more very useful constraints. Yeah, I see there's a question. Let me just finish that sentence. So we're going to now go and use this perspective of operator state correspondence of plane cylinder map to learn things about constraints on the conformal dimensions of well-defined conformal field theories. So somebody had a question.
Yeah, sorry, Julian.
Sure.
Just I'm a bit confused, but how did you get that the eigenvalues of the dilatation are real and also that they are bounded from below? I mean, they are not real energies, right?
The eigenvalues of minus I delta.
Meaning that your identification with Hamiltonian is based on the assumption that your radius is the time, but there is no a physical basis on which this is true, no?
But I can define the theory. I can define. So, what do you mean by there's no physical basis?
The reason why the eigenvalue, I mean, I think that the reason why the eigenvalues of the Hamiltonian are bounded from below and real is because they are interpreted as physical energies, or not? I mean,
I don't. I mean, I think that's. I'm not sure in what direction you're going here. I mean, the fact that they're real, I mean, this comes from hermeticity of the Hamiltonian. Well, most of the time, unless you allow this sort of PT symmetric story. But the fact that they're real comes from hermeticity of the Hamiltonian. And the fact that they're bounded from below, however, just comes from stability. I mean.
Yeah, I mean, yeah, I agree with you. But both these properties are physical assumption stemming from the fact that we are interpreting those eigenvalues with energies, with physical
No, but
energy.
I would just say that a theory that doesn't have a spectrum that's bounded from below is just unstable. There's nothing interesting there. So if there is a conformal equivalence between the theory on the cylinder and the original conformal field theory that we have, which we just established, then if one is sick, then the other will also be sick. And what I'm pointing out is that the theory viewed on the cylinder would be sick unless the eigenvalues of I delta are bounded from below.
Yeah, okay. Yeah, maybe I just missed.
I think what you're saying is that you cannot measure. There is no way of measuring the the energy eigenvalues of H on the cylinder. Is this your question?
No, probably I'm just a bit confused, as I was saying, because I missed why the radial coordinate is your time.
Mm-hmm.
I mean, because how can you identify the original time proper Hamiltonian of the system with the radial one?
No, I'm pointing out that the picture where it is most natural to think of radial quantization is the cylinder picture. So you can take some any theory that you want, let's say any CFT that you want, and you quantize it on the cylinder. And what I'm telling you is that you can identify that Hamiltonian as being the dilatation operator on the plane. There's nothing.
Your evolution on the plane is the radial evolution, not the time evolution.
Yes.
So, I mean, why you expect the generator of this evolution to be bounded, I mean, positive and with real eigenvalues?
Because it is the same. It is exactly the same mathematical object as the Hamiltonian of the theory on the cylinder.
For the conformal invariance, right?
Yes, but we're talking about conformal field theories.
Yeah, okay, no, fantastic. Yeah, as I was saying, probably I was just...
Yeah, that's the point, right?
Thank you very much. Sorry.
Yep. No, but I mean, those are important questions because, as I said, it is a little bit unintuitive, this whole radial quantization. But yes, you become more familiar with it. It becomes less strange, and in particular, it maps in a conformal theory to a perfectly normal way of quantizing the theory, which is on the cylinder. Okay. So excellent. So other questions? Then let's go to these constraints on conformal dimensions, and they are what is usually known as unitarity bounds. Now we're going to have to do a little bit more of these kind of mental gymnastics that are related to thinking about theories on the plane and on the cylinder and the implications of the conformal symmetry on that. So let's talk about something very basic, namely something that's called reflection positivity. This is just a comment of how we should think of unitarity in Euclidean signature. Okay, so this is not something at this point that is sort of tied to the CFT or radial quantization or cylinder quantization, but we will apply this notion to that series of ideas. So let's think about Lorentzian signature for a second. So a Lorentzian field phi Lorentzian at t and x, I can actually define this in terms of the Lorentzian field at 0, let's say, in terms of e to the minus I p0t minus I pjxj. This is actually the same operator that I earlier wrote, obviously e to the minus I p mu x mu, but I just want to be explicit now about the time direction, because whenever you do Euclidean time, you need to be particularly careful about that direction. E to the I pi pjxj. Okay. So now let's just apply Hermitian conjugation. So if we take this phi L at t and at x, and I apply the dagger, then Well, of course, I changed the order, but I also changed the sign of I. So this guy now comes first, but I changed the sign of I, so it looks like what's there already. So it looks like e to the minus I p0 t minus I pj xj. Then I take phi L dagger at 0, and I have e to the I p0t plus I pj xj. Okay. So that's, first of all, just generally the recipe of how I do Hermitian conjugation. So I can just naively apply the Hermitian conjugation on this operator here, and then these shift operators stay the same. Please just hold your question, Adrian, because last time I lost my train of thought.
Yeah, okay, no
Finish
problem.
this argument, and then you can, okay. Good. So, but what it also means is that if phi L of 0 is Hermitian, then this is also just literally true for the time evolved one. So phi L of t and x dagger is then also equal to phi L of t and x, right? Because I can just take away the dagger here, and I can compare it to this guy, and I see that it's the same thing, so this relation holds. Now, in Euclidean, okay, of course, t is equal to minus I tau, and now you already see that there is going to be a little bit of a snag in the story. I mean, just a slight complication, because the reason that this operator, if I put it in front and conjugated it, became this operator, is that I had here a factor of I, but that factor of I is now gone because it multiplies this minus I. So what happens is the following. It happens that, well, first of all, of course, we need to identify what is our Euclidean operator. Well, phi of tau and x, of course, must be defined to be the Lorentzian operator at I tau of x, right? Notice that I'm just writing it in terms of tau because this is eventually what I want to get to. But you could have also written this guy would be I Lorentzian time, and then this would be just Lorentzian time. Okay, so phi Lorentzian at tx. Well, just write it. Okay, tx, and then we have here itx. Okay, right. And so this means that this same relationship here now must be written by in phi of tx dagger is now equal to phi of minus tau x. So the conjugation in Euclidean space involves a reflection in the time direction. Okay, and this is why I have a reflection in here. So this is very important, and we will follow that lead. But now maybe Adrian, is now a good time to ask your question?
No, it's okay. I was confused about a sign, but I understood now. It's okay. Thank you.
Ah, okay. Very good. Best case scenario. So, so what we have learned is that conjugation in addition sends t to minus t, or tau to minus tau, excuse me. So this is this time reflection. And so when people talk about unitarity in Euclidean, when people talk about the notion of unitarity in Lorentzian signature, so things like U dagger U, or psi dagger psi, so the absolute square of a state is positive, then if you go to Euclidean signature, you have to also reflects in the time direction, and that's why people call this reflection positivity. Okay, so this is the notion of conjugation in Euclidean signature gives reflection, and then positivity becomes reflection positivity. And that was a general statement. So this is something anyway in quantum field theory that is an important notion. But what I would like to do is now I would like to see what this actually means for our cylinder slash radial slash just RD plane story. Because I've written on purpose, I've been calling this coordinate here tau, because I want to say what is now the conjugation operation on the cylinder. What does this mean actually on the R coordinate? So let's trace this back through our various coordinate systems. So we have tau goes to minus tau. And this means that R has to go to 1 over R, right? Because log R, excuse me, maybe it would be better to write it here. Log R goes to minus log of R, right? So log 1 over R, okay? Actually would have been better to, this is kind of illegal to do this, but okay, so it's a bit like that. Okay, so tau goes to minus tau means log R goes to minus log R, so R has to go to 1 over R. And then if you think back of what is R in terms of the coordinates on the plane, well, this means that xi goes to, is the inversion xi over x squared. Okay, because that's the same as R goes to 1 over R. It's the inversion transformation. And maybe to confuse you, finally, completely confuse you, actually even in Lorentzian signature on the plane, I can do this operation. It's not relevant for right now this discussion, but you know, this operation, inversion operation, of course, also I can do it in a Lorentzian plane. But okay, so what it means is that conjugation the dagger operation, oops, I want to, is an inversion in radial quantization. Okay, so let's see what happens, for example, to the operator p mu, or if you want, you know, pi. As I said, on the level of operations, you know, inversion, you can do it in Lorentzian or Euclidean signature. This is kind of up to you. Okay, so let me just write it because we're more familiar with writing it like this. So p mu is minus I d by dx mu. Okay, but this will have a non-trivial effect now because x mu, right? I have this explicit x mu derivative here, and x mu goes to x mu over x squared. So, well, what happens with this d mu? Well, it's just, that's just a, so d by dx mu goes to d by dx primed mu. Okay, just notation-wise, oh, I'm getting a micro delivery. So d, can you guys see this? Does it, I mean, does the screen share also show the notifications I get?
It does, it does.
Yeah, yeah, okay. All good. So d mu goes to d mu prime. This is just the same notation. I've said this before. So, all right. So therefore, d mu primed is just, sorry, and let me say that x primed mu is of course equal to x mu over x squared. Okay, so d by dx mu primed is equal to x squared d mu minus 2x mu x dot d. And to verify this, I have put on the problem set. That's actually a pretty easy computation. So p mu goes to p mu primed, which is equal to minus I d mu prime, so minus I x squared d mu minus 2x mu x dot d, which is actually somebody we know very well. This is k mu. Okay, so the operation of inversion, which is the same as conjugation in Euclidean signature on the cylinder, actually maps p mu to k mu. And again, maybe if you think back, this doesn't surprise you a great deal, because I pointed out way back, well, actually it's just 2 weeks ago, I suppose, that we can think of k mu as being the same as a momentum, like a translation, conjugated by an inversion. Remember I said we do inversion, translation, and inversion back, and that's precisely the special conformal transformation, generator of which is k mu. And so another way of the way that this pops up is that if we invert, then the momentum operator becomes exactly the k mu operator. So, well, the consequence of this is just noted p mu dagger is equal to k mu. And k mu dagger is equal to p mu. And the meaning of this is, I repeat again, the meaning is that we think of the theory as quantized on the cylinder, and we apply something like conjugation. And then we want to know, what does this mean from the point of view of the plane? And this is maybe also in response, or further response to David's question, right? So now we're asking for all of these constraints of positivity and so on the cylinder, because on the cylinder, we can think of this really as Hamiltonian evolution in the way that we would usually like to think about Hamiltonian evolution. And so, for example, we can ask, what does positivity mean? What positivity of the norm, or reflection positivity of quantities in this theory? What does that mean for the theory on the plane? And so this is what we're going to do. Let me try and get there. So in similar fashion, one can actually show that J mu nu dagger actually says J mu nu. This is quite nice. You can, I think that's also on the problem set. And for D, you have D dagger must be minus D, so it's anti-Hermitian, as was anticipated at some point by Adrian today. Yes, I would just ask you to fill in those details, because I'd rather go on to showing some unitarity bounds. So let's get to the bounds. Okay, but I think the principle is clear, because I showed you how to get to this relationship, and this is exactly the same thing. In fact, it's sort of trivial, because R goes to 1 over R, then R d by dr has to go to minus R d by dr. Can we hold, well, okay, no, let's have questions. Anyway, sorry, I have 10 minutes. I have 10 minutes because I, for technical problems, started a bit late. Yes, let's start with Sergio, maybe.
Yes, I was just wondering, these relations that you wrote there on the CFT in the plane, Minkowskian or Euclidean, or on the cylinder, or valid everywhere?
These are, so what I wrote is the CFT on the plane and in Minkowski signature, but the same relations are true if you put the Euclidean indices I.
Yeah, okay, thank
you. Adrian.
So is there maybe a confusion in notation? Because also the momentum generator, for example, is an Hermitian operator, right? So I would be tempted to write P dagger equals to P.
No, but that's what I said. This is what conjugation on this in the cylinder picture means on the plane.
Yeah, I see. Mm-hmm.
And the notation is, yes, the notation is a little bit confusing, but.
Okay.
So good. So let's look at a scalar primary state. Let me call it delta. Okay, so this is the state that I get by acting with an operator O delta primary at the origin on the CFT vacuum. Now, let us assume that that state has positive norm. Okay. And let's look at what happens to the level 1 descendant. So let's look at a descendant. Let's define psi mu, which is just p mu acting on delta. Okay, so now what we know, of course, is that also this state should have a positive norm. So let's look at what is the norm of this state. So let's compute the norm of psi mu squared, which is psi mu, where psi mu is equal to psi mu dagger. Okay, this is the dagger of the bra is the dagger of the cat. So okay, so we write this as actually just written it like that before. So this is psi mu dagger psi mu, which we can write as delta, excuse me, p mu dagger. Let's not go too fast. P mu delta. I'm not summing over mu, okay? I'm just taking the inner product of this for a given mu, let's say. So now this is of course equal to, according to what we said, delta k mu p mu delta, which we can write as delta into the commutator k mu p mu, right? Delta. So now if we look back, this commutator k mu p mu, we know what it is. K mu p nu has some term which is something like eta mu nu times d. I think there is a coefficient 2i. Yeah. So plus another piece which I don't have in my head now, but it doesn't contribute. It annihilates delta. So it must be equal to j, right? It must be the angular momentum. So for a scalar, it's not there. So what I get is, therefore, I get delta minus 2i with a minus sign d times delta. Okay, this is putting this here. And so what I get is 2 delta, okay, d acting on delta gives me I delta. So I get 2I delta times the norm, of the state delta squared. So now this norm, okay, better be also greater than 0. Okay, so we have here, we started with a norm here that we want to be greater than 0. Okay, and now we have reduced it to 2 times delta times something which we already know is greater or equal than 0 because it's another norm. Okay, or let's say it's greater than 0. Let's just assume that is not a null state. It's greater than 0. I said that before. Okay. So therefore, delta better be non-negative. Okay, by unitarity, or if you want, reflection positivity. So this shows us that in this theory that is unitary in Lorentzian signature, or reflection positive in Euclidean signature, the conformal dimensions are in fact bounded below by 0. Okay. However, actually, we can do more. Okay, maybe that's the last thing that I want to show you, which is actually a stronger bound exists. Okay, so proving that is also on the sheet, but I will just outline how it works. So let's look at a guy that is actually a level 2 descendant. But I look at a particular one where now I am summing p mu, acting on delta. Okay, then what I find is that 0 less than or equal to delta, and now I have k mu, and here I have a p nu, let's say p nu, acting on delta. And this can be massaged, and the conclusion will be, as you shall do in the problem set, that delta should be greater than or equal to d minus 2 over 2. Okay, which is what people really call the unitarity bound. So this is the unitarity bound. For a scalar operator. Okay. And I guess that I have 2 comments on this, 3 comments. One is that it's the optimal bound. What do I mean by this? I mean that it would have been natural to say, oh, well, we went to level 2, that gave us something stronger. If we go to level 3, it'll give us something that's even stronger, and so on. It turns out that no. By considering higher descendancy, you can still not get a stronger bound. So this is for a scalar operator, this is the optimal bound. That really is the unitarity bound. So every conformal dimension in a healthy conformal field theory has to be greater than or equal to d minus 2 over 2. We've met this, okay? It's actually the same dimension as the free scalar in free scalar, which had saturated by free scalar, which is d minus 2 over 2, okay? So free scalar saturates unitarity bound. And then the last comment is that we've said this is for a scalar, and actually you can, with a bit more work, show that there is delta is greater than or equal to L plus D minus 2 for a non-scalar operator. So this is the non-scalar unitarity bound. And what's important, this might already irk you, but actually L is equal to 0 does not recover scalar bound. So this is not, you have to treat the spin 0 and all other spins separately. Okay, this is just a comment. Okay, don't be perturbed by this. These are correct. Okay, it's just that you do not get the scalar bound just by putting L is equal to 0 here. And finally, so here we had that a free scalar saturated this bound. Actually, in general, you can say that this bound is saturated by a conserved spin L current. So conserved spin L currents saturate unitarity bound. This will play some role in what follows. In particular, we will look at spin 1 and spin 2 cases. Okay, so here we are. So this is actually what I wanted to say about conformal field theory, basically the global part of the conformal field theory. So focusing on the global part and dimensions d greater than 0 mostly. And so next week, we're really going to start into this ADS-CFT territory. We've basically now laid the groundwork that will allow us to go pretty quickly to ADS-CFT. Okay. So are there any questions?
I have one quick question, actually.
Yes, yes, please.
Could you go back to when you derive the reflection positivity bound? Yes. So I think I missed the detail here, because in the commutation relation between K and P, there's this metric eta mu. So this metric, is it Lorentzian?
No, I think it has to be Euclidean. Yes. So I should have.
Right.
Yes. I don't want to. Yeah, don't want to rewrite everything, but that's right, because otherwise you have a -1 in the 0, 0 component.
Mm-hmm. Yep. Okay, just wanted to check that. Okay.
Yep. Davide.
Yeah, sorry, Julian. I have a question for the next slide, the last one you've written.
Yep. Mm-hmm.
Yeah, what are the implications of these bounds on anomalous dimensions? Is this a meaningful question, do you think?
Actually, I do think it's a meaningful question. But so, for example, you know that the conserved spin L currents don't pick up an anomalous dimension. I don't know off the top of my head of an argument to relate this to the saturation of the unitarity bound, but I would not be surprised if there weren't such an argument.
And this is also true for the scalar field?
Well, for the scalar theory, it's sort of trivially true. There we know it because, you know, you don't have any anomalous dimensions. But for a conserved current, it's less obvious, but I think it's also true that the things are related. Yeah.
Thank you very much.
Okay, if there are no further questions, then we'll reconvene on Tuesday as usual. And those of you who are interested in taking the exam, I haven't yet uploaded sort of all of the papers. Some of them are already there, but I shall do so certainly by the end of this week. And I think I'll send an email around just giving a little bit of a description of what papers there will be and so on. Okay, see you guys. Bye-bye.
Thank you, bye.
Thank you. Goodbye.
Thank you. Bye.
Thank you. Bye-bye.